In this lecture also, we will continue our discussion on magnetic ceramics. Earlier we have considered general properties of magnetic phenomena, many different types of magnetic materials. We have also discussed briefly about the ferromagnetic ordering, antiferromagnetic ordering as well as ferrimagnetic ordering. Today we will start with our discussion on hysteresis loop, which we have discussed briefly in the previous lecture. This was already shown and presented. So, we have a hysteresis loop both in ferrimagnetic as well as ferromagnetic materials, and the details or the basic reason is that we have a spontaneous polarization both in ferromagnetic and ferrimagnetic ordering, and the in absence of any external magnetic field H, the magnetic induction or polarization is 0, and as we increase the magnetic field, it increases non-linearly with increasing field. The initial permittivity permeability is here, that is the slope of the initial curve, and that is the mu I, the initial permeability, and then of course it follows a nonlinear behavior, and finally it reaches a saturation magnetization or the maximum polarization. And as we know, as we have seen in case of dielectric material, ferroelectric material in particular, this behavior comes from the domain structure. We have a large number of spontaneous magnetic moments and their order forming a domain structure. We will discuss what is exactly the domain. Briefly it has been shown here. These are the 4 domains here having the orientation of the magnetic moments in different directions. So, statistically we have a 0 magnetic polarization, even though in the microscopic scale we have some net magnetic polarization. And as we apply the electric magnetic field, the domain starts moving, the domain wall starts migrating in such a way that all the magnetic moments slowly try to align themselves with the direction of the magnetic field, that is in this direction. So, more and more domains follow this particular orientation, or in other words, the domains with favorable orientation tries to grow at the expense of favorably oriented domains. So, at the end the saturation magnetization or saturation polarization corresponds to a kind of single domain with the orientation of the magnetic moment in parallel with the magnetic field. So, that is how the microstructure changes from a large number of domains, then one or few domains grow at the expense of the other, and finally we have only a kind of single domain. And as you have explained earlier, once we reduce the magnetic field, then this domain structure more or less continues to stay there until and unless we apply a negative bias or negative field, so that to neutralize this structural change or domain structure change. So, that is why you do not the reverse curve do not follow the same curve as in the forward direction, but the reverse curve is different, and you have remnant magnetization as well as coercive field, which we have discussed earlier. So, primarily it is the domain wall movement which is responsible for the the ferromagnetic or the antiferromagnetic hysteresis curve. With this we go to the what is exactly a domain structure, how much details we know about the domain structure. This is the kind of domain structure we have. For example, this is a single domain, the whole material, this is the material in which only one magnetic direction is there, only one direction, all the moments are aligned in a particular direction. So, it is a single domain material, and the magnetic lines of force goes outside the volume of the sample or the volume of the solid. So, ultimately it emanates from the north pole, goes to the south pole, or and this way, since there is the magnetic lines of force cannot go or cannot be neutralized here, it goes outside. Next one is a two domain structure, in which on the left we have one domain, on the right another domain, and one can see the left one is the magnetic moment is pointing upwards, whereas the right one, the magnetic domain or magnetic moment, the resultant magnetic moment of that particular domain is pointing downwards. So, there is a 180-degree rotation, and there is some lines of force outside this solid, outside the sample, but the number of lines of force has certainly reduced because they have neutralized each other. Part of it has been neutralized each other. So, this is a what we call this a domain wall. This is a boundary between the two domains, and that is called the domain wall, and also known as the block walls. This block walls. Okay. So, this since across the boundary there is a 180-degree change in the orientation of the magnetic field, not the magnetization or magnetic moment of this material, then this becomes your 180-degree domain. That is how it is designated like that, 180-degree domain wall. In the next structure we have 4 domains, and that is a very typical domain wall structure, where you have 2 domains side by side, and then there are 2 other domains comes in, one at the top and one at the bottom, and one can see the orientation of the magnetic moment here is horizontal or perpendicular to the 2 domains we had earlier. So, this is perpendicular in this direction from left to right, and here it is right to left. Okay. So, this is one domain and this is another domain. So, in all about 4 domains having orthogonal orientation between each other, and that is a very typical domain structure in a rectangular piece of magnet or magnetic material. This boundary is however different. This is 90-degree boundary or domain wall, because across this the orientation is at 90 degree to each other. Orientation of the dipoles or orientation of magnetization is 90 degree to each other. So, these 4 walls 1, 2, 3 and 4, all these are 90 degree domain walls, whereas the middle one, the vertical line, is actually 180 degree domain wall. This is also possible. More and more domain walls can be formed depending on the it want to release the internal stress and internal energy. So, depending on that, each single domain can be subdivided into a large number of domains, and there are more number of 180 degree domains now, and you have more number of both 180 degree and 90 degree domains are possible. So, this is how the domains multiply depending on the structure, depending on the situation, depending on the field and its history. Now, these domain walls, although we are talking about a changeover from one direction, one orientation to the another orientation, but this domain wall is a finite thickness, okay, like this. This is a particular wall, 100 degree domain wall. On this side, right side, you have magnetic moments are oriented upwards, whereas on the left the magnetic moments are oriented downwards. So, there is a changeover from upward trend to the downward trend, and so it is a 180 degree domain wall. But if you look at the cross section or the width of this domain, they have a finite width. This domain wall has a finite width, and this dW is the width of this domain wall, and particularly for cobalt, a ferromagnetic material, the width is about 60 nanometers. Okay, it is around 600 angstroms. So, one can see that there is about 250 atomic distances or interatomic spacing. So, there are more number of, so there is a gradual changeover, one can see here. This is completely downwards, then there is some amount of change, and then it is almost horizontal here, then it rotates still further, and finally on this plane it is perfectly parallel or opposite to each other. So, there is a gradual changeover of the domain of the magnetic moments across this domain or within this thickness of the domain. So, it is certainly it is not a sudden change, but it is a gradual change, and the thickness depends on many different parameters, many extrinsic parameters, and also the crystal structures, the lattice parameters, and of course, the kind of magnetizing ions it has. So, these are the two things one must understand, that we have domains in a ferromagnetic, or same thing happens in ferrimagnetic also, and there is a domain wall. They can be designated as 180 degree, 90 degree or 45 degree angles, and domain wall, there is a concept of domain wall. So, that there is a finite thickness within which this changeover takes place in a gradual manner. So, that is all about the domain wall. We have also seen that while we are plotting the hysteresis loop or hysteresis curve by applying electric field, applying a magnetic field slowly, the domain wall moves. For example, if you are starting with this, a combination of 4 domains, it is changing, taking into consideration that the applied field is in this direction. So, whichever is preferred orientation, so that will grow. So, you can see this has grown, this has further grown, whereas the other 3 are slowly disappearing, or the size of those domains or area of the domains are reducing, whereas the other area is increasing. So, it is not that a completely new domains are generally created, but the existing domains, some of them grow at the expense of the others depending on their original orientation. So, that is how, so it is a kind of nucleation and growth phenomena. So, whichever is preferred orientation will grow, and which are not preferably oriented, they will slowly dissolve or disappear. So, that is the concept of a domain growth with increasing magnetic field. Now, while the domains are moving in their path of the movement, they may encounter different kind of defects. The domains are moving, basically if there is a changeover of the atoms are changing their orientation, and particularly the magnetic moment of those atoms or ions, but in the process as if a wall is moving from one end to the other, and it may encounter, in addition to the normal structure of the normal lattice points or the lattice ions, it may encounter certain point defects which we have discussed earlier. There are point defects, there are line defects, there are surface defects, and so on. So, when such kind of defects are encountered in the path of the movement of the domain wall, they get hindered or they act as an obstacles. So, any presence of lattice defects, either vacancy, interstitial, or a solute atom of a different type, all of them acts as a hindrance to the movement of the domain wall, and domain wall movement is restricted as long as the domain wall movement is restricted, which means that the magnetization is restricted. Okay. So, the magnetization restricted means you need more and more energy to magnetize it. In the reverse manner, when you demagnetize it, the presence of these defects also hinder the reverse movement of the domain wall, and therefore, once they get magnetized, it becomes difficult to demagnetize, or in other words, you need higher coercive field to bring the magnetization in the to the level of 0. So, presence of these lattice defects of different types, whether it is a grain boundary, whether it is point defects, vacancy, interstitial, substitutional ions, all of them have some role to play so far as the domain wall movement is concerned, and this is getting reflected, this gets reflected in the area of the hysteresis curve. So, if we are talking about a very thin hysteresis curve, for some applications if we are looking for a very thin hysteresis curve or a low energy magnetization or demagnetization process, one must have a defect free material, large grain size material, and so on. If you have a fine grain material or a large number of defects already present because of preparation condition, because of chemical composition and so on, then there is a possibility that the energy required for magnetization and demagnetization becomes large. So, you have a fatter or larger hysteresis curve. So, if you are talking about a permanent magnet, these are very important parameters one is to consider. What should be the total energy content in the material in terms of the BH curve. So, the area under the BH curve is actually measures is a measure of the energy required for magnetization and demagnetization, and how easily one can magnetize it or how quickly one can magnetize it or demagnetize it. So, the presence of the defects including the grain boundaries has a very important role to play while we are preparing the material for a particular application. This is what I have shown you earlier. This also, this is a thinner hysteresis curve, is a thicker hysteresis curve or a wider hysteresis curve, which means higher energy needed for magnetization as well as demagnetization, and this needs a very low field as well as low energy, and the energy content of the material is also low. So, with very small fields, very small magnetic field generated, one can magnetize it or saturate it or completely desaturate it like this. So, this kind of curve is very important for soft ferrite or soft magnetic materials, and these are actually hard magnetic materials. So, basically there are two types of magnetic materials. One is designated as soft magnetic materials like this, having the hysteresis curve of this nature, whereas the hard magnetic materials should have a hysteresis curve of this type. Well, with this background we come to a group of ceramic materials which are actually very important from the industrial point of view or the technical application point of view, and these are known as ferrites. Okay, these are anti-ferromagnetic materials. So, they are not metals, they are compounds, and they are all regarded as ceramic materials. They have all the other properties like ceramics because they are basically mixed oxides. There are three different type of ferrites, basically ceramic magnetic materials, and the characteristics are all of them contain Fe2O3, and that's why the name has been given as ferrites. So, Fe2O3 is one of the major components or the constituents of all the compounds of ceramic magnets. Most of them 90% of them contains Fe2O3. There will be some others, but most of them have Fe2O3. They crystallize in a number of structures. If you talk about ferrites, there are three major structure types in which these ferrites are present are available. These are inverse spinel. First of all, inverse spinel. Spinel is the most common of the ferrite structures, and earlier we have seen while discussing with the crystal structure, we had two different spinel forms. We will discuss a little bit more about that just now within a few minutes. One is the normal spinel, another is the inverse spinel. The normal spinel structure, or this particular name has been given from the mineralogy, the name of the mineral, that is MgAl2O4, magnesium aluminate, whose mineralogical name is spinel, and it forms a structure types. So, any material, any mixed oxide which crystallizes in this particular form, it is called spinel, and there are normal spinel, the magnesium aluminate is actually a normal spinel, whereas all the ferrites are actually inverse spinel. We will tell you what exactly it means. Then the second group is garnets. This is also another compound, again mixed oxide. I will tell you what is that, and then magnetoplumbites. So, there are three different crystal types in which the ferrites are available. All of them have the very important or strong magnetic property or magnetization. Spinel, the general formula is MEO Fe2O3. Okay, MEO Fe2O3. Sometimes it is also called AoB2O3, but the ferrites, when you are talking about ferrites, B2O3 is invariably Fe2O3. So, it is MEO Fe2O3, Me a transition metal oxide, normally another transition metal oxide. Iron is one transition metal oxide, and Me is also another transition metal oxide. So, the combination of two transition metal oxides, one divalent and another trivalent, forms the spinel structure. Garnet, it is also a very important group of magnetic ceramics. This general formula is 3Me2O3, a trivalent oxide, and also another trivalent oxide, but Fe2O3 is again common. This is also Fe2O3 in spinel ferrites, and garnet ferrites also has Fe2O3, but the ratio is different. It is 3:5. So, Me2O3 in this case, this trivalent oxide Me is not a transition metal, it is a rare earth, it is another group of compounds which has some amount of similarity with the transition metal so far as the electronic structures is concerned. Me is actually a rare earth metal, or Me2O3 is a rare earth metal oxide. So, the alternate formula one sometimes write Me3 Fe5O12, okay, Me3 Fe5O12, it is the same thing which has been written here, only thing it is here is total oxygen is 9 into 15 24, here it is only 12. So, half of the molecular formula here. So, this is the two ways of expressing the Garnet structure. We will discuss a little bit more about that. And the third group of the ferrite, which is also very important from the practical point of view or industrial point of view, is magnetoplumbite, and the general formula here is MEO6 Fe2O3. So, the formulas are different, the ratio of Fe2O3 to other oxides are different. Here it is 1:1, here it is 3:5, and here it is 1:6. So, MEO in this case is not a transition metal or rare earth, it is actually a divalent metal from the group 2, and like barium oxide, calcium oxide, copper oxide, strontium oxide. So, either BaO, CaO or SRO. So, this is what we call the magnetoplumbite structure, and because of this ratio 1:6, sometimes it is also designated as hexaferrites. Ferrites, of course, there is another reason also, because it has a hexagonal structure. These two have a cubic structure, these two have a cubic structure and this also as a hexagonal structure. Well, to give you little more information about the ferrites, the spinal ferrites are isostructural with the naturally occurring spinel, which I have mentioned just now, Mg spinel, which is the MgAl2O4, and conform to general formula Ab2O4. Relatively large oxygen ions for this spinal ferrites are arranged in cubic closed packing with octahedral and tetrahedral interstitial sites occupied by the transition metal ions. Okay. So, the divalent transition metal ions occupies some of these sites. We look at the structure little more closely. And the Garnet structure, the rare earth in the rare earth, yttrium iron, one of the major the important components or the members of this Garnet family is yttrium iron garnet, okay, where rare earth is yttrium, iron is anyway there, Fe2O3, and then it is called yttrium iron garnet or YIG. Is prototypical of the rare earth ferromagnetic insulators. So, it is a rare earth ferrimagnetic insulators, not ferromagnetic insulators, and yttrium is a rare earth cation, and it can also be replaced by other cations, like one of the other members is gadolinium, Gd, gadolinium iron garnet. Looking at the structure of ferrites, this is the representation of the structure of the ferrites, spinal, particularly the spinal structures. The spinal, as I mentioned, it is Ab2O3, Ab2O4 structure, and in which oxygen forms the closed packed cubic structure. Closed packed cubic structure. In any closed packed cubic structure, you have two different interstitial sites. One is the tetrahedral site like this, having 4-fold coordination, and other is the 6-fold coordination, the octahedral site. So, here also you have octahedral sites as well as tetrahedral sites, and the two cations A and B have their preference of going to one of the particular interstitial sites. So, in a direct spinel structure, all the A cations goes to the tetrahedral sites. So, A plus A2 plus goes to the tetrahedral sites, shown here as a second bracket, and the square bracket here represents the octahedral site. So, this represents the tetrahedral site and this represents the octahedral site. So, the Fe2 sorry Fe3 plus ions in a ferrite, of course, ferrite has an inverse spinel. If you are talking about normal spinel like MgAl2O4, so Al has octahedral coordination, so it goes to the octahedral, and Mg2 plus goes to the tetrahedral sites. That is the description of the spinel in direct spinel. In inverse spinel, it changes out of the two B3 plus cations, one goes to the tetrahedral site and another remains in the octahedral site, whereas all the A sites all the A cations or 2 plus cations comes to the octahedral site. So, that is the redistribution happens, and that is the typical of what we call the inverse spinel. Incidentally, all ferrites containing Fe2O3, which we have discussed just now, crystallizes in the inverse spinel structure. So, ferrites means inverse spinel structure, not the direct spinel structure. So, this is the octahedral distribution of the blue ones are the oxygen, and this is B cation in case of direct spinel, and both A and B cations in case of inverse spinel, whereas in the tetrahedral site you have only either A cation or B cation, both depending on whether it is direct or inverse. Now, since we have talked about that it is a general formula AB2O4 type, A sites is here, or in ferrite structures, if you are talking about ferrites, cubic ferrites, we have MEO and Fe2O3. So, both Fe and Me in principle can be substituted by other cations. So, if we are talking about the A site, Me site, it is 2 plus basically, they can be substituted by large number of different divalent cations. Some of them are non-magnetic, they do not have a magnetic moment, whereas depending on the unpaired electrons, there is no unpaired electrons, so no magnetic moment. So, these are some of these cations like zinc 2 plus, magnesium 2 plus or barium 2 plus, they can go into this substance, but they do not have the magnetic moment, whereas other magnetic cations like Mn2 plus, Ni2 plus, CO2 plus or even Fe2 plus. The other site is Fe3 plus, but this site can also have Fe2 plus as in as for example in Fe3O4. So, Fe3O4 is basically a combination of FeO and Fe2O3. So, that way this site A site can have Fe2 plus as well. So, these are magnetic substitution by magnetic cations, and these are substitution by non-magnetic cations. Similarly, in the B site, Fe3 plus site, you have one chromium is magnetic and aluminum is non-magnetic. So, these are possibilities. So, there are isostructural, what we call the isostructural substitution, there are extensive isostructural substitution is possible in case of spinal ferrites. And correspondingly, you have different properties, different compounds, both magnetic properties and as well as other physical properties. Now, let us look at two other structures which we have just mentioned. Garnet structure 3 Me2O3, 5 Fe2O3, or in other words one can write Me3 Fe5O12. Me, as I mentioned, a rare earth ion which may be yttrium or sometimes gadolinium, both are normally used. Now, the way the structure is represented here, the structural sites can be called P, Q and R. So, these are 3 different interstitial sites in this. Okay. In this case also there are a large number of oxygen ions compared to 4 oxygen ions there. We have 12 oxygen ions here in the formula, and you have again it forms a cubic closed packed structure, and there are it is not exactly a closed packed structure, but cubic symmetry. So, there are 3 different kind of interstitial sites. Okay. Earlier you have seen there are 2 interstitial sites, one is tetrahedral and octahedral. Here there is an additional interstitial sites which has a 8-fold coordination, it is called dodecahedral coordination, and particularly the rare earth ion goes and sits in that. So, in addition to the other tangent metal cations, Fe3 plus particularly, the rare earth ion has a different coordination. So, it is not a 4-fold coordination, it is not a 6-fold coordination, it is actually a 8-fold coordination of the oxygen ions. So, we have an additional interstitial sites here, and they are sometimes also designated as C site, A site and D site. Sorry. P cations, that is primarily the yttrium or the rare earths, goes and have an 8-fold coordination and is called sometimes C site. Q is an octahedral coordination, and the iron ions go and sits there, a 6-fold coordination, and R is the tetrahedral coordination or with 4-fold. So, these are also the designated as sites. Okay. One of the reason we have discussed earlier, in a ferrimagnetic ordering, there is antiparallel ordering. Okay. The atoms, the magnetic moments of the neighboring atoms have an antiparallel ordering, but as because that the magnitude of the magnetic moments are different. So, we still have, they do not cancel each other, unlike in an antiferromagnetic material, where the because of the antiparallel ordering and the magnitudes may becoming same, the net magnetic moment is 0, whereas in ferrimagnetic material, the spinal structure either in spinal or in garnet or as also in hexaferrites or magnetoplumbites, you have a unequal magnetic moments which have antiparallel orientation, and because of this antiparallel orientation we have always a net magnetic moment in a particular structure or in a particular formula. That is what it also happens in case of garnets. Instead of 2 sites, you have 3 sites, A, D and C sites. So, their magnetic moments are different. So, A and C are parallelly oriented, whether both of them are antiparallelly oriented with D. Okay. D is the tetrahedral site. So, that is the origin, and that net moment, there is a net finite moment or finite magnetic moment which comes, and so it becomes a magnetic material as such. So, just like any other ferrimagnetic material. So, garnet structure is also very important from the point of view of ceramic magnets. The other one is in hexaferrite. Well, the details are not fully there, except that they have a hexagonal symmetry, and the formula we have already discussed. The compounds either barium hexaferrite, calcium hexaferrite or strontium hexaferrite. So, all of them more or less have an identical property. All of them have hexagonal symmetry, unlike spinal and garnet which have cubic symmetry. Here is an hexagonal symmetry, and all spins are parallel in any particular basal plane. So, when you are talking about a hexagonal structure, it is basically a kind of layered structure, AB packing, and you have basal planes which are actually perpendicular to the C axis, or it is actually AB plane. So, AB planes are not normally called the basal planes. So, in all these planes, basal planes, the magnetic moments are parallelly oriented. However, neighboring basal planes will have different cations, and they have a different magnetic moments and also antiparallelly oriented. So, unlike in spinel and garnets, each individual ions are antiparallelly oriented. Here each individual planes are antiparallelly oriented. So, one particular plane is having a parallel orientation, all of them are directed in the same direction, or the magnetic moments of all the atoms, all the ions are directed in the same direction, whereas the neighboring planes have a different orientation. So, it is a antiparallel orientation, but of a slightly different nature. All that is what it is mentioned, all spins are parallel in any particular basal plane. The spins in the neighboring plane are also parallel, but in opposite direction. So, the antiparallel ordering is of a slightly different nature. And because of the hexagonal symmetry, in this case it is not a cubic symmetry. So, it is highly anisotropic, the properties are highly anisotropic, and C axis is the preferred direction of orientation. So, if all the magnetic moments are oriented along the C axis of the crystal, it becomes very difficult to realign it to other directions. And because of this anisotropic property, these hexaferrites or magnetoplumbites have a high or very large hysteresis loop, and therefore, mostly they are used as permanent magnets. Okay. They are not soft magnets or soft ferrites, they are primarily permanent magnets or hard ferrites. So, all hard ferrites or permanent, whenever we talk about permanent magnets of the permanent ceramic magnets, we invariably talk about the hexaferrites or magnetoplumbite structures. So, since they have a very preferred orientation or anisotropic property, the microstructure is also very important. So, microstructure is another very important property to be controlled to have the desired property of these materials. Well, with this discussion, let me go through look at there is a simple way to calculate what should be the saturation magnetization of a spinal ferrite. Particularly for spinal ferrite, I am taking only one example here. How to calculate the saturation magnetization, what will be the maximum when all of them, all the domains are oriented in a particular direction, what will be the maximum polarization we expect or magnetic flux density one can expect. That depends on the individual magnetic moments. So, this is what one can find out. MNO, let us say we are taking an example of MNO Fe2O3. We can write the formula in this fashion, considering the sites where these particular ions are sitting, whether it is the tetrahedral or octahedral. So, outside this square bracket, this means it is the tetrahedral site, and inside the square bracket means the octahedral sites. So, the octahedral sites, and keeping in mind that it is an inverse spinel, so there is a redistribution, half of the Fe2, the B site, half of the Fe2 is in octahedral, half of the other half is in the tetrahedral site, and all the A atoms are in the octahedral sites. So, that is the description of how these ions are distributed between the two different interstitial sites. Then one can write theoretical magnetic moments of these ions is this has already been discussed earlier, and there is a list here. You can see from the Hund's rule, one can find out, not this one, sorry, this one, yeah. So, the different cations have different number of d electrons, unpaired d electron, 3d electrons, and accordingly to Hund's rule there are number of unpaired electrons actually give rise to the magnetic moment. So, one has to find out what will be the unpaired electrons here. Up to 5, this will be the same as the total number of electrons, whereas from this side once it is 6, it actually become 4. Okay. The unpaired electron becomes 4. So, accordingly you have a list of calculated magnetic moments in terms of the Bohr magneton. How many Bohr magnetons will be there? This expression also have been introduced to you earlier. So, with this Fe3 plus has 5.92 Bohr magneton. Okay. Fe3 plus is a 5. This is actually D5 ion. Okay. There are 5 unpaired electrons. Okay. So, since it is D5, it is 5 unpaired electrons, and this manganese 2 plus also has 5 unpaired electrons. Okay. Here it is manganese 2 plus and Fe3 plus, both of them are D5 d5 electrons, and since d5 according to Hund's rule there will be 5 unpaired electrons. All of them are actually unpaired. So, this is the magnetic moment of this ion, and this is the magnetic moment, same in fact, both of them are same. So, the net magnetic moment per formula unit, again theoretical, is because there is an antiparallel coupling or antiparallel ordering, this and this actually cancels each other. Okay. If this is pointing upwards, this should be pointing downwards or vice versa. So, this Fe3 plus and this Fe3 plus actually cancels each other. Okay. So, it is minus 5.92 Bohr magneton, and within bracket this is also 5.92 from manganese, and this is also 5.92 for the iron. So, ultimately the resultant is 5.92 Bohr magneton. Okay. So, this is a very simple way to calculate what is the expected or theoretical value of the maximum magnetization or magnetic moment you can expect in a structure like this. And so, the experimental value in fact is close to that, but it is slightly different. Instead of 5.92, it actually varies between 4.6 to 5.0. Of course, all these variations are there primarily because of the different external extraneous factors. So, this is one way how to calculate in a very simplified form what is the expected magnetic moment of these kind of systems. Following that, there is a list here, there is a table which has been given here for different kind of ferrites, different system of ferrites. For example, this is zinc ferrite, and in fact, this is not a inverse spinel. Okay. It is also, although it is called zinc ferrite, but this is not, does not have a magnetic property, because it is a not a inverse spinel, it is a normal spinel, and zinc is outside and 2 Fe2O3s, Fe3s are inside. So, there is hardly any interaction between this side and this side. So, although they have net magnetic moment, but the theoretical value is 0. Okay. They have a antiparallel orientation. This is Fe3 copper ferrite. Okay. This is copper ferrite, and it is the copper ions magnetization which is reflected in the overall magnetization property or magnetic moment. So, whatever is the copper ions magnetic moment, that is the overall magnetic moment of that particular compound. Same thing, this Fe3 and this Fe3 cancel each other, and then it is 2.83 here, and I will get about 2.4. Fe3 plus, here is cobalt ferrite. Cobalt ferrite is actually again the same thing, it is the magnetic moment of cobalt which gets reflected here. Fe3 plus cancels each other. Fe3 plus, this is magnetite, and once again that of Fe2 plus actually gets reflected here. Here it is Fe3 plus and manganese ferrite. So, once again it is the manganese ions magnetic moment which gets reflected here, which is the maximum because this is 3d5. Now, there are many solid solutions, there are many solid solutions here, and right, please note that change, please note that change. Fe, this Fe and this Fe will cancel each other because of the antiparallel orientation ordering, whether zinc 2 plus, if we go to the table here. You can see zinc 2 plus is actually a 3D10, zinc 2 plus, copper 2 plus, all of them are the 3D10 element or ion, and therefore, there is no magnetism. Okay. There is no spin magnetic moment, therefore, it is 0, and that is the reason zinc ferrite will have a 0 magnetic moment, and this Fe3 plus and this Fe3 plus will cancel each other. So, that happens in all of them. The Fe3 plus, one atom or one atom is inside, or one ion is inside the or in the octahedral side, the other is the tetrahedral side. So, they cancel always each other because they are in antiparallel ordering. What I was telling is magnesium, this is magnesium ferrite, and we have here magnesium is in the both the sides, inside as well as outside, and that makes a little different here. You can see once you add magnesium into the, so most of it actually goes inside, but part of it is there outside in the sense in the tetrahedral side. So, magnesium gets distributed between tetrahedral and octahedral sides, and as a result iron also gets redistributed between the octahedral sides and tetrahedral sides. Okay. So, which was 1:1 distribution, now it has become 0.9 and 1. So, because of the magnesium substitution, and then as a result you have a net magnetization which is of the order of 1.73, but the actual value, experimental value is about 1.10. So, this kind of isostructural substitution and looking at the structure itself, one can calculate, one can really predict how much magnetic moment one can expect and what will be the saturation magnetization, right. So, for all ferrite is the structure which is important, and this kind of simple consideration gives you the magnetic moment of the overall material. This is just a reference, this was given earlier, and in all these cases you have to remember this is the formula which has been used to arrive at these figures, okay, because there are integers only so far as the number of electrons are concerned, but only when you use this formula the integers are different, it is no longer integer and some fractions comes up. So, this relationship you must also remember. Well, we are talking about the calculation of the magnetic moment of different structures, particularly the spinal structure we have already considered. Here is some kind of data particularly for the other two types of structures, the hexagonal ferrites or the magnetoplumbites or sometimes magnetoferrites they are called. So, barium hexaferrite the experimental value, it is difficult to calculate here. Spinal, it is not as easy in case of spinal structure. Spinal structure it is relatively easy to calculate, whereas magnetoplumbite structure it is not so easy so far from the consideration of the crystal structure point of view, but the experimental values are here. It is BaO Fe2O3 and SRO 6 Fe2O3 is 1.1. Once again there is some problem. This should be Garnet. Okay, I will change them. These are actually Garnet structures. So, the distribution of EG as we have mentioned earlier, this is in the dodecahedral site, and this is Yeah, this is ABC kind of structures. I'll discuss them later on, maybe. Okay. So the garnets, these are all garnet structures, and then we have some binary oxides. Some binary oxides also has some magnetic properties. Particularly, one important thing is about chromium oxide. Chromium oxide is extensively used for tape recording and so on. So they have also some magnetic properties. I think we will discuss them little details in the next lecture. Thank you for your attention.